Let's draw the Lewis structure for the hydrogen peroxide molecule H2O2. I'll leave the steps up on the screen. Let's determine how many valence electrons we have to work with. Hydrogen has one valence electron and there's two of them. Oxygen has 6 valence electrons and there's 2 of those. It gives us a total of 14 valence electrons. Now we're going to put oxygen in the central as the central atoms because hydrogen can not be the central atom. And we're going to need to make 3 bonding pairs to connect all the atoms. So a bonding pair is a pair of electrons participating in a shared covalent bond. So let's reduce our total valence electrons from 14 minus 6. We have 8 valence electrons remaining. Next, let's complete the octet on the terminal atoms. Now the terminal atoms are hydrogen, so they already have a duet. They've already achieved the octet rule, so we'll put the remaining electrons on the central atoms. Let's put 4 each on each of the oxygens, and that uses up the remaining electrons, and we have achieved the octet rule for all 4 of our atoms. Now, you might have also considered putting making something like this, which appears to follow all the rules as well. But when you have more than one possible structures, you need to consider the formal charge. And what the formal charge will do is it kind of assigns a charge to each of the atom in the molecule. And the way we can do that is to take the total number of valence electrons in its neutral atom and subtract the number of dots, which is the lone pairs, minus the number of connecting lines or dashes, which represents half of the electrons in the shared bonds. So let's get the formal charge for that oxygen on the left. Oxygen normally has 6 valence electrons. I can see 6 dots there, minus 1 dash is going to have a -1 formal charge. Now this oxygen, the next one, has 6 valence electrons in its neutral atom, minus the 2 dots is the lone pair, minus 3 dashes, which represents the shared electrons in the covalent bonds, and you get +1. So already this is not a favorable structure because it has formal charges all throughout the molecule. You want a molecule with formal charges of 0 or close to the charge of the molecule as possible. Finally, let's take a look at what the geometry might look like, because it's this is a flat screen, and this is not what it looks like in 3-dimensional space. I'm going to copy this over so I get some more room. All right, now let's take a look at the central atom here in the oxygen. It's going to have 1, 2, 3, 4 electron regions. When you have 4 electron regions, or regions of electrons, the parent shape is tetrahedral. But not all 4 are connected to other atoms. Only 2 of them are. So we have 2 lone pairs. So the geometry of the molecule around that central atom is going to be bent. So if we can draw this a little bit more accurately, it might look something like this. The oxygen, the hydrogen, and the hydrogen there, and we are going to try to, now these are all on the same plane, and we're going to try to separate these lone pairs with as much separation as we can. So this one's maybe coming out at you, right through the screen in kind of an angle, right at you. So there's a lone pair there, and then there's one going behind the screen. That's a lone pair there. That is not Doesn't look right for some reason, but we got one here going behind the screen, and then we have one coming right at you here. Okay. In any case, these and these are trying to get max repulsion. Now, what just happened? Okay, here we go. All right, maybe a simpler version would be like this, without attempting a 3D. Okay, and so bond angle here is less than 109 degrees.